All right, in this video, we're going to take a look at the property of solubility and how it compares or how it's determined by intermolecular forces. So in the last video, we had done this table to look at boiling point property and how it can be explained by intermolecular forces between molecules. There's a great challenge one for you to try here, so I recommend you try this out and try to pick which of these two molecules here will have the higher boiling point and justify your prediction. Hint, it might help to draw in your vector arrows for your dipoles. This is a good challenge one. It's a nice, good practice one here. And then over here is just a summary table for the intermolecular forces and boiling points. So it's a bit tough to understand what's going on right now, but if I start to explain it to you, you'll pick up on it pretty quickly. So here we have a bunch of molecules, and they're only made up of C and H's. And so you'll see they have some differences in boiling points. And you'll notice that these over here, if they're only made up of C and H's, that means they're non-polar. And so you would know that the main intermolecular force is probably going to be London dispersion. So why are their boiling points different? Well, maybe there's more London dispersion in one compared to the other. So there's probably more London dispersion in here compared to here or here. Now, this is a bit difficult to understand at first, but it has to do with their shape. The more linear they are, the more points of contact there are for London dispersion, and so that's why there's a higher boiling point for this compared to these ones here. So more linear means more points of contact. But the point is that you would be able to tell that their differences are probably due to LDF because they're nonpolar. Now, if you come over here, you'll notice that you have these molecules here. They have differences in boiling points. They both do LDF because everything does, but you'll notice there's a big difference here. Over here, this one has a 78 degree Celsius boiling point, and this is negative 25 degrees Celsius. So you can probably guess that it has something to do with this OH. This one can do hydrogen bonding, whereas this one can only do dipole-dipole. And if you were comparing these three here and you had to guess which one had a higher boiling point, a lower one, and the lowest one, well, you can probably guess that this would be the lowest, this would be the highest, this would be in between. Lowest Y, non-polar, only LDF. Highest Y, polar, OH group, hydrogen bond. In between, well, it's polar, so at least it can dipole-dipole, but just not quite as high as hydrogen bonding. And so if you can justify at that level, you're on a really good track to understanding these concepts overall when it comes to melting points and boiling points. So now we're going to take a look in this video at how intermolecular forces affect dissolving. Here you have a glass with some water and oil in it, and if you try to mix them together, they won't mix. They'll eventually separate into layers. Water will stay at the bottom, vegetable oil will stay on top, and that's because water is more dense than oil. Being less dense allows you to float on top of something more dense. But why is it that they don't mix? Well, it has to do with their polar and nonpolar natures. Water is polar. Oil is just a bunch of CHs, as you can see, so it's nonpolar. And the general trick is that like dissolves like. Polar will dissolve other polar or ionic things, and nonpolar will dissolve other nonpolar things. Since water is polar, it will not dissolve oil, which is nonpolar, because they're not like each other. To be able to interact with each other with hydrogen bonds or ion dipole forces, you need to both have polar parts to you. If there's no polar parts, like in oil, it's not going to interact with something polar. So nonpolar will interact with nonpolar, and polar will interact with polar. So here we have an example of dissolving happening. There's a great video I do want you to watch later on that explains dissolving, but I'm showing dissolving for ionic compounds and also for molecular compounds. So salt, NaCl, ionic compounds will dissolve in water. And the reason it dissolves in water is because ionic compounds are basically very, very, very polar. They're extreme versions of polar. So when you put them in water, which is also polar, is going to surround and separate the ions. That's called dissociation. That's where you separate the Na and the Cl minus. You're moving them away from each other. They're still technically together. They're just separated by water molecules now. And so what happens here is the partial negative oxygens surround the positive sodium, and the partial positive hydrogens surrounds the fully negative chloride, and these are called hydration spheres. And so what happened is when you put the NaCl into water, the water molecules will surround the ions according to the attraction, and that's called a dissociation. The ions will separate. Okay, and so basically what happened is the water disrupted the ionic forces, and ion dipoles forces formed between the water and the ions based on the rules of attraction, with the partial negative to the positive and the partial positive to the negative. And so the ions actually physically separated. Now, polar molecules can also dissolve in water. This was an ionic compound dissolving in water, ions being separated, but polar molecules can also dissolve. So here we have basically a clump of sugar. These are all sugar molecules, sugar, made up of a bunch of atoms, okay? When you put them in water, notice the water will surround them as well. The water will hydrogen bond with the parts of the sugar that can hydrogen bond, usually OH groups. But notice that it doesn't separate. The water is not separating the individual atoms of sugar, okay? So there's no dissociation. Dissociation is really, for example, for ions separating. The Na and the Cl will separate from each other. They haven't decomposed, they've just moved away from each other. So here, the individual atoms of the sugar have not separated. It's just you're separating the individual sugar particles. So water surrounds this, water surrounds this, water surrounds this, but we're not going to break it apart even more. So essentially, both of these can dissolve. Salt can dissolve in water because it's ionic and water is polar. And then sugar can dissolve in water because, well, sugar is polar and water is polar. Like dissolves like. Understand the process that with ionic, there's dissociation that happens. The ions are separated because the waters will surround the different ions using their partial charges. When it comes to molecular compounds that dissolve, they need to be polar first of all, because like dissolves like. But the molecular compound itself will not separate into smaller pieces. It's just this molecule will be separated from this molecule. They'll move away from each other, but the individual atoms will stay within. So basically what's happening here to dissolve the molecular is that the water is going to separate these, going to disrupt some dipole and LDF that's happening between the sugars and form some dipole and hydrogen bonding between the water and the sugar instead. So it's like you're trading off. Initially, the sugars were all interacting by dipole LDF, and now the water is going to interact with the sugar by dipole H bonding. And you could say LDF too, but it's really the H bonding that's doing that there. No covalent bonds are breaking here. Okay, no covalent bonds are breaking here. And over here, no ionic bonds are really breaking. They're still there. We're just sort of separating them. So we are putting some space between the ions so that the water can surround them. But technically speaking, they are still there and attracted to each other. If you were to evaporate the water, they'd come back together into solid form. So the rule again is like dissolves like. Polar solvents dissolve polar solutes, including ionic. So water can dissolve salt and sugar because they're both ionic or polar. Non-polar solvents dissolve non-polar solutes. So if you look over here, water cannot dissolve hexane. This is hexane, it's non-polar, water is polar. Water cannot dissolve hexane. But if you put hexane in oil, chances are it would dissolve. Here we have an alcohol that has an OH group, and here we have water. That OH group makes this alcohol polar, and so the water can interact with it with a hydrogen bond and do some dissolving. Basically, to dissolve, you need some good interactions, and the only way to do that is if you have like dissolves like. So here we have sugar will dissolve in oil, or will not dissolve in oil, but does in water. Why is that? So here we have sugar and oil, it's not dissolving. So you know that oil is non-polar. So if like dissolves like and sugar won't dissolve, that means sugar is probably not non-polar. Sugar is probably polar instead. So sugar is highly soluble in water because sugar is polar. It has these OH groups that's able to hydrogen bond with water that will surround it. So how do we predict relative solubility? That basically means how do we know if something's soluble in water or not, or how do we know which one's more soluble in water if you were comparing different compounds? So generally, polar compounds have a higher solubility in polar solvents than non-polar compounds. Okay. Now, if you're comparing nonpolar compounds, they have low solubility. And the larger the nonpolar parts, the lower the solubility in water is going to be. Okay. So let's do an example here. Here we have butane and butanol. These both have very polar parts to them, or very nonpolar parts to them, all those CHs. But you'll notice there's no H here. So this OH makes this a little bit more polar. And so because this is a bit more polar, chances are this butanol would have a higher solubility in water compared to this butane here. If we look over here, we have BH3 and NCl3. You would figure out which one's polar or not. If you do your work, you'll see this is nonpolar and this is polar. So the one that's polar should be more soluble in water. So you would say NCl3 has a higher solubility in water. So let's go ahead and fill in our blanks and recap some of the important information that we just saw. So we were taking a look at the rule that like dissolves like. Polar solvents dissolve polar things because you have more hydrogen bonding capabilities with polar solutes. Non-polar substances will dissolve in non-polar solvents. And generally, the larger your non-polar parts, the lower your solubility is going to be in water. So oil is nonpolar, NP. That's why it will not dissolve in polar water. Whereas something like sugar or even alcohol is polar. So here we have alcohol. It's polar. And because water is polar as well, the water can dissolve the alcohol. And so we know it's polar because of this OH group here. And then water is polar. We know that now. Here we have an example of hexane and water not mixing. They're not mixing. And so that's because hexane is nonpolar because of all the CHs there. And water is polar. If you took hexane and put it in oil, chances are it would dissolve in there because, well, oil is nonpolar. It's a bunch of CHs and water is polar, but hexane is nonpolar, so these would dissolve. Okay. And our final table here, we have comparing substances based on their solubility and boiling points, and we'll do those. But first I want to do the molecules down here. So rank the molecules according to increasing solubility in water. And so we want to show which one's more soluble in water. They all have OH groups. So they might all have some degree of solubility. But remember that the more nonpolar parts you have, the less soluble you are, because you're almost like oil. So this has a really big nonpolar part. That's probably not very soluble compared to this. So the smallest solubility would be the octanol, because it has a very big nonpolar part. Then the butanol, because yes, it has a big nonpolar part, but it's not as big as the octanol. And then finally, the methanol would have the highest solubility in water. Methanol, because its nonpolar part is much smaller. So this is a large nonpolar region. This is a small nonpolar region. It's the smallest one in that group there. And so this table here really is a summary of everything we've seen so far. And let's go ahead and try to do these. So you should pause your video and try this out, and then take a look and see if you're on the right track. So I'm going to start with solubility first. I'm going to say that in the pair here, butanol, or 1-butanol, is the most soluble, and that's because OH makes it polar. And when I say soluble, most soluble, I should specify in water, because if it was oil, it would be the opposite. If it was oil, the non-polar one would be more soluble. All right, between butanol and propanol, they both have OH. However, which one would mix with water more effectively? I'm going to say propanol. And the reason that is because it has a smaller non-polar chain or part. It only has a 3-carbon chain. Between BH3 and NCl3, we've done that one already, but just to try it again, NCl3 is more likely to dissolve in water, and it's simply because it's polar. But BH3 is non-polar. Let's go ahead and look at the next one, NH3 and CH4. So by now we've done these examples quite a few times, but NH3 is likely going to be the one that has a higher solubility. And that's because it's polar. But CH4 is non-polar. And remember, the rule is not like dissolves like. So polar will dissolve in water more effectively than something non-polar. And lastly, we'll compare ethane 1,2-diol and ethanol. So which one is more soluble in water? Well, they have the same length of carbon chain. So they have the same non-polar regions. But notice that ethane 1,2-diol has more OH groups. So I'm going to go with that one. Ethane 1,2-diol. And then the reason is it has more OH groups, allows for more H bonding with water. So that was the solubility piece. Let's take a look if we can do the boiling point piece. So back to the top, the highest boiling point of all these, I would say, is butanol, because it not only does the same amount of LDF, but it also has hydrogen bonding. Now, between butanol and propanol, for boiling point, butanol, because yes, it has H bonding, but so does the other one. The main reason is that it has more LDF since it's a bigger molecule, since larger molecule. Between NCl3 and BH3, well, NCl3, and that's because it is polar, so it does LDF plus dipole-dipole, and it does a lot more LDF because it's a bigger molecule. But the dipole-dipole is the main reason. Between NH3 and CH4, higher boiling point, NH3, it's polar, and it does LDF plus H bond, but the CH4 doesn't do H bond, it just does LDF. And then for the boiling points between ethane 1,2-diol and ethanol, I'm going to go again with ethane 1,2-diol. And that's because, yes, it can do LDF, plus it can do more hydrogen bonding since it has a 2 OHs. So notice that there's no memorization, but it's more because of OH groups. I'll put 2 OH groups. It's more application of the information as opposed to memorization. So you need to understand what makes you more soluble in water is being polar, so you can have more hydrogen bonding capabilities with the water solvent. And then what makes you a higher boiling point is, being polar, hydrogen bonding, all those reasons there. And so this is a great summary table to test your skills with the different properties. And just do make sure that you review the process of dissolving for both salts and for both ionic compounds and polar compounds. And remember that nonpolar compounds won't dissolve in water, but they can dissolve in nonpolar things. And that concludes our intermolecular forces lesson, along with how they determine properties of various substances that we deal with.